Good. Okay, now let's start from the presentation. Yeah. So I'm a presenter here, but it's a work of many people, all groups, so easier was to just put, because we are coming now from Plasma-PEPSC project. Is a main developer of BIT1 code now, and we are in the IPP, so we have people from IPP and Ljubljana, so who are BIT1 team members. So on behalf of them, let me discuss BIT1 introduction to this hackathon. Now, there are some people, at least remotely, who are not very familiar for particle in cell simulation, so I will give some short history, and then I will discuss what are the specialties of the BIT1 code, and then we'll see how we distribute our training. So first plasma simulations probably were done by Buneman and Harlow, so in 50s, and these are two people given here, and they were done in probably one of the first supercomputer, which was doing 10 kiloflops, and it was a big achievement. It was 10 to 1,000 particles, and I would say that it was a big achievement at that time. And this was particle-particle codes. So particle-particle codes scale with n squared, so when n is number of particles, and if you put just, let's say, remember 9 particles, and you just only 20% of interactions, it's already becoming messy. So it shows that if you want to have a particle-particle code, it's very time-consuming, and probably records are of the order of million particles or 2 million of them. Now, this is not the right way to go because it's not sufficient. We have to simulate 10 to 13 particles, sometimes even more. And we had to introduce a new way. It was particle field codes, so particle in cell codes, when particles are generating fields, so macro fields. These fields are acting on the same particles and advancing these particles, and this was called particle in cell simulation. And here, PIC scaling, just from the particle side, scales as a n is number of particles, and we have at present 6-dimensional electromagnetic particle in cell codes capable to simulate up to 10 to 13. So the probably pioneers of this approach are Dawson and Birdsall and Hockney. Probably definitely know this Birdsall and Langdon and Hockney's book. And I was happy to collaborate with Mr. Birdsall. It was very interesting and very, very useful collaboration. He was coming to Innsbruck for training us for his code, so but it was different kind of training, I would say, yeah. Now, and also code BIT1 is actually based from one of the oldest codes, particle in cell codes, because it's based on XPTP1 code for Birdsall's laboratory, and it's very flexible. Although 1D, it's very flexible, so it's adjusted for needs of the users. So what is particle in cell? So those who don't know, particle in cell, you have a point particles which move under given, equations which are well known. So in the charged particles, so plasma are charged particles, and charged particles suffer the electric field and just magnetic field actions. The problem is whenever you have point particles, it's very easy to advance particles, but it's not so easy to get corresponding charge density and currents, because in order to solve equations of the field, you need the equivalence of the kind of some spreads or the special distribution of these, and point particles will never work with this. So you need to do some extrapolation from point particles to grid cells, because in the numerical simulation, at least all the PIC simulations, we have grid cells, so space is gridded, time is gridded, and the main principle of PIC approach, each particle gives its credentials to nearest points, grid cells. So in other words, it weights these grid cells. In other words, assigning particle density and charge, the current to each point. And depending how many grid points you assign or weight, you have different accuracy of the simulations. So initially simulations were done with zero order, so nearest point, but then it was not okay because when particle was going from one to another grid, it was jumping. So it was not okay. So when I had time for the, let's say, students, I have these pictures, how it changes, jumping from one to another, but it's not okay. So if you go to the next step, so when 2 points are weighted, you can have first order, and then the particle gives weight to nearest 2 points or grids, and it gives as much as it is near to these points, and then you have quite smooth transition. Of course, you can increase accuracy with more if you weight more points, but of course, this is done in the price of the simulation time. So usually it's the optimum in first order, and some codes have the possibility to switch to order, second order, and so on. BIT1 is localized here, so first order. And also in our case, we have only first equation, Poisson equation, so it's electrostatic code. Now, how more detailed picture of the particle in cell codes. So as I say, you have particle mover, which advances particles in time, having these equations for velocity and acceleration. And then if you have no collisions, you have weighting of particles to grid. So you have to give their density or current density to each grid cells. Having these densities, so having their points, grid points for given charge and the current densities, you can solve Maxwell equations, and then you have to recalculate, because you are getting from the Maxwell equations the electric and the forces on the grid points, and you have to recalculate forces on particles, so it's inverse weighting. And then these particles are feeling this field, the forces, and then this is this whole cycle. But at least for fusion plasmas, is definitely not sufficient. You have to take into account the nonlinear and inelastic interactions, and these are done by Monte Carlo routines. When particles are colliding, in our case, we have BIT1 has a very large part of the Monte Carlo collisions. It has a non-counter-based Monte Carlo model, which means it's fast, has no limit on collision types. I will have a separate presentation on this topic tomorrow. And then this part has to be included. So what are the specialties of BIT1 is that, first of all, it has a physics-based Poisson solver, which is accurate, is extremely fast. It's 1D, but still very fast. It's funny, it was not easy to find one-dimensional fast solvers, while 2 and 3D were quite available. Then it has natural sorting. Natural sorting means that it has optimal use of cache hits. So it's very easy for space decomposition whenever you want to go to massively parallel simulations. And also it has no limitation on system size. Maybe I will spend some time tomorrow on what does it mean, no limitation on system size. It has stress cross-section model. I think it's the only kinetic code worldwide you can capable to do non-coronal approximation for high-density plasmas. And in fusion plasma, at least for next generation machines, we will have high density, extremely high density plasma, 10 to 21, 10 to 22, and this has to be taken into account. And disadvantage, of course, we have also disadvantages. All the classical codes is numerical noise. There's any classical particle SEN, and I am to say that you have numerical noise anytime. Even some codes are energy conserving. They have energy non-conservation unless you correct this energy conservation. It's very easy to demonstrate because velocity is proportional to the electric field, and and should not be zero. So the average of these values, velocity, and also the oscillation, so of the velocity as well as electric field are zero. So this value is zero. And you have all time this inaccuracy, even round of error. So it's all times place. But whenever you consider quadratic value, if you got quadrat of the electric field oscillation, it's not zero. Also, this means that also velocity is not zero. And if velocity is not zero, it's in analogy with the diffusion. So if particle is in average, the motion is, the position change is not zero in square, this generates diffusion. And diffusion in velocity space is same as numerical heating. So it means that one has to take care that numerical heat will not arise. So good for edge particle codes is that particles are at some point disappearing at the wall, and so they disappear with their mistake. So this is good thing. Now it's quite old sketch from one of the invited talks, and shows how these plasma edge simulations for fusion-related plasma were developing. So probably started in the 70s, Tagizuka Abe, so then Kodura, so those people who introduced first, probably one of the first kinetic simulations of the scrape-off layer. This was one of the first famous paper about plasma sheaths, and so on and so on. And the number of particles per time step, which is the main measure of the size of the simulation, was increasing and increasing, and definitely there were huge codes like VPIC and some others who are somewhere else. So why we need these codes? Because they can help to formulate boundary conditions and study stability problems, which cannot be, some of them cannot be treated by fluid or gyrokinetic codes. They can treat non-local parallel heat transport, which cannot be treated by a fluid approach. They can calculate particle and heat loads to the plasma-facing components, and if they are time-dependent, this can be done by only these codes. They can study drift effects when the drifts cannot be approximated by classical drifts, if so the gradient scalings of the non-uniformities of the order of gyre radius, and many other problems which need particle in cell simulations. Now, coming back to coming back to BIT1 code. So BIT1 code simulates the scrape-off layer. So those who don't know this, if you take a tokamak, so this is torus, and make a cut of it, you get so-called last close flux surface, which is called separatrix, which is just this white, so the border of this white area is separatrix, and everything outside, almost everything outside is called scrape-off layer, and so we simulate scrape-off layer. And this scrape-off layer is a very important part of the tokamak because it defines fluxes defines practically fluxes coming to the plasma-facing components and also out of the plasma-facing components. So it defines lifetime of the plasma-facing components, and also on the other hand, it defines the performance of the plasma, because you have too many impurities coming to the core, then degrades your performance of the plasma. So it's very important place to study. And in BIT1 considers 1D approximation of this, so from inner to outer divertor, it has a particle and the heat source corresponding to the plasma and heat transport from the, let's say, inner plasma to scrape-off layer. So you are injected particles here, they propagate as in scrape-off layer towards the divertor plates. When they reach divertor plates, they initiate plasma surface interactions, and then these injected atoms and molecules interact with plasma, and all this is simulated by BIT1 code. So it's at this moment it's highly scalable, but there are near exascale attempts now to develop of this code. So it's a part of the Plasma-PEPSC project here. It has nonlinear energy and momentum conserving collision operators. This is very unique. What has BIT1 code, it can simulate collision of 3 particles or simulate 2 particles, which go into up to 5 different particles, and all times energy and momentum is conserved. It has linear energy and angular dependent plasma surface interactions. Linear because we do not consider time scales when your surface changes. So we have plasma particles are treated in 1D, and can be also in neutrals in 2D, and impurity can be quasi 2D if you remove impurities from the simulation based on the anomalous transport coefficient. Code outputs can be any, just any profiles and velocity and angular distributions, and also has a synthetic diagnostics, quite simple to get from the distributions. Usually it goes, the massive, let's say, heavy simulations, we use more than, few, let's say, at least few million grid cells in one direction, which is very difficult for the stability issues. And it's very flexible. Why it's flexible? Because sometimes you simulate in one machine, then you can easily take simulation results from one machine, put in another machine. You can use different CPU number. You can use different simulated particles. You can add particles during simulations or restarting simulations, or just cut out some simulated species from it. You can split particles. So it was during all these probably more than 25 or 28 years, we try to have as flexible as possible codes, because just to adjust to make as fast as possible simulations. Of course, it's very interesting that it has also natures like external circuit. So you can put biasing of different diverters, you can put currents going, so different regimes can be directly simulated by input file. Now, if I go to next, few results from this code. So these are distribution function of electrons at the diverter plate, and showing high density, low density cases in our next machine, so Compass upgrade. And these are presented recently in one work package meeting. It just shows that you can easily get practically any accuracy distribution functions, because we needed to get these tails of distribution functions which carry heat and energy. And so there are not no special simulations or special diagnostics. Usually, typically, your accuracy of distributions for reduction at least 10 to minus 7. But if you make a special code, special simulations, you can increase accuracy up to 10 to 8 and 10 to 9. So another example is, for instance, what I put it here, for instance, the collisional sheaths. Using BIT1, we find out a new regime of the plasma sheaths, which is we call collisional sheaths, which appears in high density plasma, and it will play a very important role in next generation fusion reactors or machines, because density will be very high. And very important point of this collisional sheaths, that plasma is not sonic, so subsonic. And all our existing codes, any fusion codes assume sonic plasma at the sheaths, which is not the case. It appears to be not the case for the high density next generation machines. So this was also obtained by BIT1, and maybe one of the examples of time dependent simulations. Actually, we simulate, Ljubljana team usually simulates blobs. We simulate ELMs, so ELMs and blobs are some time-dependent events when high-density plasma or high-pressure plasma propagates along the field lines to the diverters, and this is how density in the from inner to outer diverter changes in time, and distribution functions showing that distribution of the particles of velocity distribution is very different from the Maxwellian. So you have two branches, thermal and high density, high energy. And if you take, for instance, cutoffs to see it directly, so the initial, it's not really, it's quite near Maxwellian, but then when ELM comes, so high energy branch arises, and then when ELM stops, it slowly relaxes to the let's say Maxwellian one. And these simulations, for instance, one of these predecessors of our simulation is used for ITA. So ITA diverter design takes this into account, and so although it's 1D code, is very, very heavily used still. Yeah. Now I'm coming to few points which we have to take in account. PIC simulations are very nice, but there are some known limitations and some unknown limitations. So let me briefly summarize them. So first of all, known limitations. PIC simulations or classical PIC simulations resolves plasma oscillations, so it should be very small number, so delta T times omega plasma. Then if you want to resolve cyclotron motion, then your second condition on time step is that cyclotron frequency times delta T should be much smaller than 1 or smaller than 1. In order to resolve Debye shielding, and we are simulating plasma, you have to, your grid size should be smaller than lambda Debye. Because plasma is connective, just a complex system, so you have to have at least 10 particles per cell, and as much as you have is better, of course. And then comes to numerics, so numerical conditions, so current conditions. So it means that if you have a fastest particle, during one time step, it should not jump over few cells. So it should go only one boundary between cells. So this is current condition. And very unknown one, which is very important and usually people neglect, it's mesh. Because if you get, usual mesh, let's say Cartesian mesh in one dimension, for instance, yeah, and if it's uniform, you can show and prove that this mesh generates no self-force. Many people ask us why you do not generate non-uniform mesh. If you generate non-uniform mesh, you can prove that it generates self-force. This is not very known, and there are many curvilinear coordinate codes which definitely generate, with high probability, let's say, self-force, but it can be very small, but this is not the case. If you go to 2D or 3D cases, there is no general solution proving that self-force is really zero. For 1D, one can find solution, and actually it should be not so difficult, probably, at least for Cartesian coordinates, to find a, let's say, solution for non-uniform mesh, but classical one is not fully correct. There will be, if you have a non-uniform mesh, your code has a self-force. That's why BIT1 is all times using uniform mesh, although if there will be some manpower, probably we can go to non-uniform mesh too. Now, all these conditions, they are not coming from just thumb, because if you can go very strict theory or particle simulations. For instance, you can develop a model of the finite size particles in a discrete space, and then your corresponding dispersion relation will have this shape, where, for instance, S is the Fourier transform of the particle shape in the usual space, so it's finite size. And then you can solve, for instance, this equation. You can find that if your delta X is of the order of lambda dBi, then you are very near to analytic solution. But whenever in this case, your delta X of the dx should be delta X, it's of the order of, let's say, in this case, 5 times lambda dBi, your real one as well as the imaginary one are absolutely different. So this shows that this condition can be also strictly obtained from the analytic models. Yeah, the same concerns all other models, conditions which we derived there. Now training. It was about BIT1. Now a few words about the training. We considered few cases. Idea that you get used to simple models and advanced users, and we can sit down with one trainers and we can make simulations of more complex and productive runs and discuss how this can be performed. But as a first step for not very experienced or unexperienced and also advanced users, we propose two approaches. One is plasma oscillation, to study plasma oscillations modes in the unmagnetized and magnetized plasmas. One can show analytically that so we have if there is a one-dimensional model, so electric field is given in this direction, that is a tilted magnetic field, you can have 3 modes of oscillation, so ion cyclotron, lower, so with omega minus, and higher hybrid modes. And we try to see, do we simulate these our simulations? So if we do not have magnetic field, all these reduce also from this equation also to plasma frequency omega p. So we have once more in unmagnetized plasmas. So for non-plasma specialists, we should get only 1 mode omega plasma, and for magnetized one, 3. On the other hand, one can also simulate more complex cases and simulate instabilities. So we have also prepared cases for instability modeling. So one of them is a plasma beam instability. So we have plasma here, and there is a small fraction of, in this case, electrons having some beam velocity, cold electrons, and corresponding dispersion relation is given here. And if we assume that the concentration of beam particles is very small and the beam velocity is much higher than thermal velocity, we end up with these expressions of the dispersion of the oscillations when we have a the real one, we have plasma frequency, and the non-real one will be some fraction of the plasma frequency. And it means that it has both signs and shows that it's unstable. So we should see unstable generation of unstable modes. And also see by Jakub presentation, he will have the similar cases, but with two streaming instabilities. Now, what we observe here, so very important to know that we have now prepared two cases. So one is with Python scripts, because post-processing is quite heavy work, even if you take simple simulations. So another is MATLAB. So I'm responsible for MATLAB, so I upload the simplest what you can get from these simulations. For instance, what I get if you draw the oscillation spectrum of unmagnetized plasma, we got this, so this is different frequencies, and we had very good match with the omega plasma. And all these analytic expressions are given in MATLAB scripts. The same is done for Python scripts, so you can do these frequencies here. If you go to magnetized plasmas, we do not see the third mode, omega, so ion cyclotron mode, because you need very long simulation to see it. It should be somewhere here, and it's not done. But we see, on the other hand, we have low hybrid and up hybrid frequencies, and also what you cannot get from the analytic model, also harmonics of the up hybrid. Yeah. If you go to plasma beam instability, this is one of the simulations. You see that, if you remember, I said that the frequency is given here, and exactly we get oscillations of this frequency which are growing on, and at some point you will see that simulation. Just the model, the plasma is becoming unstable. So these are now our future steps. We will have time to distribute people who wants which machine, who wants MATLAB or Python scripts. You got all the versions. You got also code. Implementation of code, we will help to implement this code. Those who did already, probably it should be very trivial. And I think that's time to stop for me. So thank you. Probably you have questions. You're welcome. Good. Thank you. Now then, if there are no questions, then I ask now Stefan or Jerne. Yeah, okay. Maybe you can start and do it directly from there via Zoom. And meanwhile, I will put it here. Okay, just 1 second. Stop sharing. Okay, I will try to pick up, yeah. Okay, it's telling that I cannot, so I have to stop recording. Sorry.